Hi guys, and welcome to the second part of this week. We are in week 8. We are still dealing basically with the content leading up to midterm 2. The review is available for you guys on Canvas. So we're still dealing with the last part of this unit we dealt so far as this midterm with the solar system. And today we're starting a new topic, which is actually included also in midterm 2, but it's actually going to be relevant for the content that is coming next down the road, namely the stars. So the plan is we finish light, then we start the stars by studying the sun, and then we move on to other stars and basically the classification of stars. Once we explore that, we're going to delve into some particular kinds of stars, at least one star dies, basically we will have neutron stars, black holes, white dwarfs, and those are basically the remnants of stars after they die, after they run out of fuel, basically. And then we're going to get into the group of stars coming into globular, basically clusters. And then you have, after that, you have galaxies and a group of galaxies, galaxy clusters, and things of this nature. So we'll get into the universe at the end of the day. But before we do that, we have this units of 2122 from this week that we need to finish. And then next week, we're going to finish light because we still have 3 more units after that. Yeah, 3 more units. Unit 25 is not part of this exam, which is the last part of the light, and it deals with the Doppler effect. We're going to defer that to midterm 3 because actually we're running a little bit out of time leading to the midterm. Granted, the midterm is not next Wednesday, but the Wednesday after, 2 weeks from today, namely November 9th. So this is the plan. This is where we're headed. And there was a question actually not from your group, not from this not this from Astronomy 120, but it was from another astronomy class that I'm teaching also about homework 5 and 6. So homework 5 is already assigned for you guys, so you're aware of it. So I'm planning to post a video, and I'm going to share it also with you guys on these 2 homework assignments. The plan is to do it on this weekend so that you guys have it ready for you guys while doing your homework. I'm going to go through some problems with a little bit more detail than others, but I'm hoping that 20 to 30 minutes video will be enough for you to help you do the homework. It's still, if you have a problem with the lecture, if you have a problem with the homework assignments, if you have a problem with some of the things relevant to the stuff that we're doing, please reach out so that we can have the all of the discussions, everything is resolved. I don't want to have any kind of, especially since we have a midterm coming, so this is probably a useful time to reach out and make sure that you have all of the resources needed to make sure you pass the class. This is basically in a nutshell an intro to the things. Let me quickly look into the week in here. So we have quite a few things in here. So, and I mentioned that last time. So let me share briefly the screen in here with you guys so that you look at the same things. So again, we finished units 48 and 49, and now we're dealing with 21 and 22. Those are the topics of the day today. Homework 5 is still due after the midterm, so it's still plenty of time for it, but I'm going to post a video on it anyway. And you have the quiz also, which is due after the midterm, so it's still something that's useful that you guys go through. And you have the review, which is actually due the day before the midterm. Remember that you will receive full marks just for doing the review. So it's a very useful thing to have it completed as soon as possible. And we have the live session, of course, that is from today is going to be posted in here. So this is basically in a nutshell what we have coming. We still have another homework from the next chapter, actually the next week, which is still not published. That is going to be posted. So the recording that I'm planning on doing this weekend is going to cover both this homework and the homework that is coming. So it's going to cover both of them. So hopefully you will have enough resources to complete this homework assignments. Okay. So let me find the 2 units, namely 21 and 22, and let's discuss them quickly. So let me share unit 21. So unit 21 deals with light, okay? Light is a topic that interests the humans from the get-go. People were interested in it, trying to understand it, and trying to see what its nature is. It was the early hypothesis that was made a long time ago, of course, that light runs through a straight line, just like a stream of water basically going through a full line, basically. So what is it made up of? What makes up the light? There was a theory by Alhazen, and later on that made more popular by Newton. It's the type that light is made up of tiny particles basically streaming through. And he was doing this experiment in the old days in the desert in tents. So he has a hole in the tent, and then he saw the light going straight through. So he thought that it's made up of tiny particles, and the laws of basically reflection were known at that time, even before Alhazen. So the laws of reflection and refraction. So light, if it hits a medium, a reflective medium, it's going to bounce off of it in such a way that the angle of incidence equals to the angle of reflection. This is true on a daily experience. If you look at the mirror, that is exactly what's happening. So if you look at the mirror, the light that is going to leave your hand, for example, is going to reach the mirror and bounce back to your eyes, giving you the impression that this is the hand is on the other side of the mirror. If you happen to go and look on the other side, there is no hand, there is no you on the other side. So this is the law of reflection, in the sense that the angle of incidence is equal to the angle of reflection. That is exactly what happens with the reflective mirror, whether flat or concave or convex. So that is basically the law of light. There was another law also that was known at that time before even Alhazen and Newton, and that law is the law of refraction. If you happen to have a cup of water, for example, and you dump your pencil in it, you will see that the pencil is kind of broken. It looks like on the surface where the water meets the air, the pencil tend to seem to be as if it's kind of dislocated. So, and that's not true, because the pen is still straight through. So what happened in this case, as light goes from a light medium to a thick medium, it travels at different speeds. So it appears to be breaking apart. So that was this well-known fact. And then after that, there were Mr. Young in the early 1800s, where he conducted experiments with light, where he took a source of light. Preferably, he took actually a monochromatic light, meaning like a laser beam light, basically. I'm trying to look for my laser stuff in here. It's not here. I just moved a lot of things to this room. Now I don't have, I have to find what things are. Anyway, the point being in here is that if you have a beam of light that is monochromatic, and you run it through a slit, an opening, basically, a very tiny opening, okay? So what you will notice in here is the light diffuses. This is something that you can see even on a large scale. I mean, if you're standing in front of a source of light, it's going to make a shadow behind you that is a figure of yourself. But if you move back, that shadow starts kind of become diffuse, okay? So the image starts from a sharp shadow to a diffuse shadow, because again, the light scattered on the surface that is in face of it, and then basically scatters around it. But if you make the opening so small in this case, the scattering will produce interference phenomena. Basically, you will have bright regions of light, whatever color it is. So if it's a red light, it's going to be a red light, followed by dark regions, completely lack of color, and then another bright color, which is red in this case in my example, and another lack of color, and so on and so forth. So this pattern, which is bright and dark, indicate without the shadow of a doubt that light is a wave, because waves do that. There was another experiment that Mr. Young also did, was he took the same source of light and he ran it through a couple of holes, basically called slits, separated very close from one another, and then he ran them from the other side. Now, these two act as sources of the same light that came in, but they're in phase, if you wish. They're coming together at the same time. So when they leave together at the same time. And he had a plate on the other side that collects this light. And they interfere also with dark fringes, bright fringes, dark fringes, bright fringes, and so on and so forth of light. This happens better with the same color of light. So if you use blue, use blue. If it's green, use green. If it's red, use red. Because if you use white light, there will be a bright white spot in between, and then there is all kinds of spectra that form on the other side. Basically, light breaks down into its components. But for the monochromatic light, that was easy to see the different fringes as they form on the screen that is collecting light at the end. This indicates also, without a shadow of the light, that unlike what Mr. Newton and Hazen and everybody else thought, that light is made up of tiny particles. No, light is actually made up of waves. It is a wave, okay? Which begs to ask then, what is waving? What is going on? What is going on? What is, because if you take a string, for example, and you hit the string in one end, then you know the string is going to oscillate back and forth. So you ask what is waving, it's the string that is waving. For the case of sound, for example, it's a wave also, because it travels from your source, which is producing sound, to the receiving end, which is probably the ear in this case. Then you ask what is waving? Well, the molecules in the air are moving back and forth due to the pressure exerted and released by the source. And then once they hit the end, once they hit the receiver, that pressure is the one that is going to yank the eardrum out of its location or push it inward. And that motion back and forth in the eardrum is connected to the auditory system, basically, which is a nerve in there, and that nerve will take that signal to the brain, and the brain interprets it as different frequencies with different intensities. So basically, that is how sound works. So it's the pressure or the density of the air. If you don't believe me, all you have to do is basically remove the air from a room and conduct the same experiment in vacuum. No matter how much sound you're producing, if there is vacuum, it's not going to travel. So what causes in this case what is oscillating in this case, what is vibrating, it's the air. Or if you're conducting it on a desk, for example, it's the material of the desk that is vibrating. So the question that is asked now is, what is vibrating or what is oscillating in the case of light? And the answer is electromagnetic, meaning there is an electric field and the magnetic field. The symbol for the magnetic field, by the way, is B, that they oscillate, they go back and forth. The electric field goes back and forth and the magnetic field goes back and forth, okay? And in doing so, they travel. They travel in a direction that is perpendicular to the magnetic field and perpendicular to the electric field at the same time. So that is what is oscillating. It turns out who had the answer to that was Mr. Maxwell, actually, is the one who answered that question, what was oscillating. So Mr. Young showed that the light is wave, and Mr. Maxwell showed what was oscillating. It was the electric field and the magnetic field that were oscillating, okay? Now, the problem went full circle because later on, Mr. Einstein looked at an experiment. If you take a mirror, for example, and you hit it with light, which is a wave. Now we know it's a wave. This is what Mr. Young and Maxwell has put together, okay? What happened in this case, an electron is ejected. So, and this is exactly how the photocells work on your roof if you have the solar panels on your roof, or if you see them, if you go by some houses and even some buildings, commercial buildings, now they have them everywhere. So this is what's going on. So you have a light, which is supposed to be a wave hitting an electron, ejecting an electron, and later on stored in batteries or consumed directly in the electrical grid of the place where it's used. So the question now is, this can only happen if light is actually a particle of a given momentum. So you have a momentum that hits a particle, and that particle is ejected like billiards, basically. So Mr. Einstein, this is basically, this experiments, he didn't conduct them, by the way. He tried to explain the photoelectric effect. And he then said, okay, light is actually a particle again. So we went a full circle. We went from the idea that light is a particular nature of light, or corpuscular nature of light. I should call it the way that they call it, corpuscular nature of light. That light is tiny particles, basically. That's it. He called them photons. It's Mr. Einstein who gave them that name, photons. So we went through full circle, basically what the idea was that in order to explain a reflection and refraction, light is particles. But in order to explain the interference patterns that are produced, light is a wave, and it is a wave, and you can measure its wavelength, and you can measure its frequency, and you can measure the speed of light, and so on and so forth. So everything fits in perfectly. So there is no question about it that light is a wave. But then the photoelectric effect, for example, proves without the shadow of the light that the light is actually a particle. There is another effect called the Compton scattering, and the Compton scattering involves light which is of extremely high energy coming from sources like the nuclear reactors, for example, or inside the stars. And that is, we're going to need that. Okay, the Compton scattering is extremely needed, because inside the core of the sun, for example, or any star, what's happening in this case is photons, they come with a lot of energy. And once they do, they have to scatter through the electrons, and they take a long time before they leave the sun. So in this case, light must be a particle. So what is light exactly? Well, light sometimes behave as waves and sometimes as particles. So this is the dual nature of light. So this is a duality nature of light, okay? This is actually not true only for light, it's true for everything. Even electrons, which are particles with a given mass, they do have a wave nature also to them. So everything has duality in it. Now, the question is, what is the mass of the photon? The mass of the photon is 0. Although it's a particle, it has no mass. So light has no mass. It's important because you're asking me, okay, you're telling me this is phenomenon like billiards. So if this is the cue ball, for example, that's light, and then you have another ball in there that's number 8, for example, the solid 8, then you're hitting with it. So it must collide, and that collision must require a mass. No, it doesn't. All it requires is a momentum. So light has momentum, but has no mass. Okay, that's really what this whole idea is. Now, light, and this is true for any kind of waves also. Okay, wave transports energy, takes energy from place to place. No material is moved. As a matter of fact, light travels in vacuum. Does not even require a medium at all to travel in it. And like the string, for example, where the string is actually the medium, or the air, which is the medium for the case of sound, or for the seismic waves, for example, which is the earth, which is the medium, or for the water waves, which require water. Sound does not, light does not require a medium at all. It can travel in vacuum. How do we know that? Well, the sun is 150 million kilometers away from us, and there is no material between us, yet we see it because light is traveling from it to us. So that's something in here that is needed. Another concept that we need is actually the speed of light. The speed of light was a puzzle. People tried to understand it for a long time. Mr. Alhazen actually was one of the people that argued early on that light has a finite speed. So if this is a source of light, I'm trying to draw and condense it in a light bulb in here. So that is emitting light. Then in this case, and you have a receiver in here, which is your eyesight, for example, it takes a finite speed to travel from source to receiver. But then the reason why it's so is because you said that, look, the stars must be far away, because if they're close by, and even if they should shine all the time, just like the sun is, but comparison, of course, is not there. But the point in here is that the stars, if the light has an infinite speed, then light that left the stars from everywhere, they must hit us all the time immediately, which means that it will render our day just like our night, all of them bright. But it has a finite speed. Of course, he couldn't find a way to finding it. It was the first attempt to try to find the speed of light was with Mr. Galileo. So what Mr. Galileo did was, he had a friend of his, and he took a, let's call it a candle, okay? light of source, you know, those things in there, in the old days. And he had his friend go about a mile away or another basically barn. And he was on this side about a mile away. And he told him, I'm going to turn my candle. Once you see the light of the candle, turn on yours. Okay. So now here is the deal. So here is Mr. Galileo sitting in here. So here is Mr. Galileo, big G man. Here is his friend. So he lights his candle. That's event number one. Light will travel in here, will reach his friend. By the time his friend lights his candle, light will travel back to Mr. Galileo, and Mr. Galileo times that. He didn't have a clock, he didn't have a watch, he used his wrist to see the pulses on his wrist from basically the blood pulses on his wrist. And he counted 1, 2, 3, 4, 5 until he found how much light is traveling. This distance was about a mile away. Obviously, the speed was all over the place because you know the distance, and if you know the time, then distance over time will give you how fast light was traveling. So in order to compare that, he called his friend and he told him, you know what, come closer. So they went to the same barn and now they were close to one another. So the distance is practically nothing now because they are in front of each other. He thought they were going to repeat the experiment again. He collected a lot of data, by the way. And then he did again with his friend, but this time around, they were actually next to one another. So he did the actual experiment and he found the same result. Whether you are a mile away or you are inches away, it's the same result. So at the end, he was kind of confused and he basically threw all of the data away. And he said, you know what, I really can't find this. I think what I was measuring, he said, is the reaction time, that's all. My reaction time and that of my friend, that's all. Because the same data are similar, both cases, whether you're a mile away or close from each other. So in this case, the data is useless as far as measuring the speed of light. It was Mr. Romer later on who actually came up with the first best attempt at trying to find the speed of light. Mr. Romer, basically what he did was he noted Io. At that time, Galileo has discovered the moons of Io already. So Io takes about 42 hours to go once. By the way, those sitting in Astronomy 125, that was one of the big labs that we did last week. We're trying to find the mass of Jupiter using Io, among other things. All of the other four moons, all of the 4 moons of Jupiter were involved, including Io. Again, Io takes about 42 hours to go once around Jupiter, so it's a fast enough process. So you can measure the period, actually. You can observe it and see how long it is to go around Jupiter, okay? Take your binoculars, I have some here. Which I need a mount for them, okay? But this one is actually a little bit hard to use for Jupiter because it's kind of moves around a lot. So with a telescope, I have a small telescope in here. With a telescope, you can actually track Jupiter and see its moons. Now, every 6 hours, that's what we did at the lab. Every 6 hours, you're going to find Jupiter, Io and monitor it. So that's what Mr. Romer was doing. And he collected the data. Then 6 months later, when the Earth is on the other side of the sun, he collected data again. And he theorized that there must be a light because now light is coming from Io to here. So let me draw the picture in here somewhere. Where is that? So imagine with me that the sun is here, the Earth is here when you were conducting, and Jupiter is here. Jupiter moves 12 years once around the sun. Basically, the Earth goes 12 times around the sun before Jupiter goes a full circle. So after 6 months, the Earth will be here. And Jupiter will hardly move from its position. So this motion is really negligible compared to the position of the Earth. So the 6 months later, light that took this distance only to reach us now takes this whole distance to reach us. Okay? Takes 2 times the distance between the Earth and the sun, which is 300 million kilometers in extra to reach us. So he calculated the shift in frequency, basically how long the period of Io as it moves around Jupiter, And he found the speed of light, basically how long light takes to reach us from this 300 million kilometers. That's the shift actually. And he found the speed of light, c, to be around 200,000 kilometers per second. That was the first serious attempt in trying to find the speed of light. It gave us a ballpark. It's not an exact number, but it is a very, very good approximation that Mr. Romer did. Then after that, Mr. Fizeau came up with another experiment. He had a light source, like a laser beam, and he had a gear mounted on a device that spins. So try to draw, let's draw a circle and then with gears. Okay, it's much easier probably. And the separation between the gears, he knows exactly how much it is. It's part of his experiment. And he ran it, he let it spin. On the back of it, there is a reflector material. So the source is on this side. As it's going through between the gears, it's going to hit the reflector and bounce back. So he kept on adjusting the speed of the gear until light will go in and basically come out from the other side. So the gear will spin just enough so that one gear will come out on the other side. Based on the geometry involved in here, based on the ratio of this spinning gear, and based on the distance that is involved in here, he was able to find the speed of light that is almost 300,000 kilometers per second. This is the known value now, the speed of light. Further refined experiment of Mr. Fizeau later on led to this better value that we know today, 299,790 something kilometers per second. So light has a finite speed, okay? But then, as I was talking about earlier, with a source of light, just like sound is, it diminishes with distance, because if you have power that is an output in here, you're going to move away. The same energy that was emitted in here will drop like 1 over square of the distance. Why? Because it was over a whole sphere of this radius. Now it's a bigger radius. So wave travels on a sphere. So as the sphere grows, then that same light or that same sound or that same wave now is spread throughout the entire new sphere. And the sphere's radius is 4 pi times the radius squared. Hence the light drops like 1 over distance squared. I mean, think about it. If you're close from a tower that is for your cell phone, you will have all the bars. You move away, and the bars drop and drop and drop and drop. And it drops actually 1 over distance squared. If you have a light source, for example, a candle, and you're close from it, you can read off of it. If you move away, let's say 10 meters, you're hardly going to read off of it, but the light is still there. If you move 100 meters, about stadium basically length, you're going to probably see a dot on the other side. And if you move, for example, a kilometer or 2 kilometers or even 10 kilometers or 100 kilometers, you're not going to see that light at all. So it drops like 1 over distance squared. It's going to be part of that fades completely out. So that's an important result in here, trying to understand it. And describe how light interacts with matter. That is something that we already discussed, the reflection, but light also can get absorbed by an atom, for example, and that excites it. When the atom is excited, it wants to go back to its ground state, so it's going to re-emit it. And it may re-emit it in the same frequency as it absorbed it, or emit it by cascading to where it started from. So the light that you send to an atom may be too much to jump it all the way to a much higher energy level. But then as it goes down, it could make the same jump and then emit the same frequency, or go through stages before it emits that, before it reaches the ground, in which case it's going to emit lower frequencies, longer wavelengths as it comes down. So again, this is in a nutshell what we're talking about in here. So what happened to the mouse in here? I have only one screen, but I don't see the mouse in here for some reason. Oh, because of this. Okay. So again, the speed of light is 300,000 kilometers per second. And it's the vibration of the electric field and the magnetic field. This is the combination work of both Mr. Young and Maxwell. Maxwell is the one who basically, it's actually, Maxwell summarized a lot of the equations basically that were done at that time, and he came up with Maxwell's equations, which are Faraday's equations, Ampere's law, and there was somebody else. lens also was involved in those experiments, and Coulomb's law, which later on Mr. Gauss gave it a different form. So it's Gauss's law. And Mr. Maxwell basically fixed something with the Ampere's law, and then he put them all together. And he solved them. And that's when the electromagnetic waves were discovered. And there was suspicion, actually he was suspicious. It looks awfully similar to Mr. Young's experiment. Was light an electromagnetic wave? That's what he was faced with. It was later on Mr. Hertz actually who did that work and actually confirmed the work of Mr. Maxwell that indeed it is an electromagnetic wave. Okay, electric field and magnetic field. So again, the electric field is going up and down, and the magnetic field is going left and right. You're wondering what happened to me? I'm sitting in my room right now or somewhere else, and I'm outside, and the electric field is everywhere. If it's true, if you're telling me then light is an electric field, why I'm not electrocuted? Well, here is the reason why. You have this light that has this electric field going this way. I'm sorry, let me drop it this. Going this way, you have another light that is going this way, you have another one that is going this way, so at the end they cancel on average. Okay, their net effect is that they cancel every which way, so that's why you're not electrocuted. And if you use a polarizer, then the electric field can point more or less in the same direction. Okay. Then the magnetic field, if you're worried about it, don't worry about it, because it's, I mean, it looks of the same proportions in here, but if the electric field is this much, the magnetic field is 300 million times smaller than the electric field. That's why our eyes, when they receive light, they really respond to the electric field, but they really don't care about the magnetic field, because the magnetic field doesn't. So there are electrons in the retina and the on the retina skin basically itself, there are the electrons that respond to the electric field, and depending on what frequency hits them, they could go up and down fast or small. If they go fast back and forth, that electrical current is taken by the electrical nerve, I mean by the optical nerve, to the brain, and the brain interprets that as being either a blue color or a violet color. But if they move back and forth slow, then in this case, the brain will interpret that that's a red color or a yellow color or something, tells you that this is what you're looking at. And then depending on the intensity, if they go back and forth, far or far, back and forth, depending on the frequency, then it tells you this is a super bright, either a blue color or a super bright red color. So that's how the optical nerve basically interpret the, I mean, send the signal to the brain, and the brain gives you basically how the colors look like. If the frequency is too high, first of all, the electrons do not respond to the retina, so you don't see that color. For example, for the ultraviolet or the X-rays or the gamma rays. Or if the frequency is too low, again, the electrons, they would not respond to it. And what you're looking at in this case are the infrared or the microwave. If it's an infrared, actually, you will feel the heat coming because your skin will respond to it, because there's going to be heat that you're going to feel. Okay. So this is in a nutshell what the electromagnetic spectrum, or what the electromagnetic light is. Again, I discussed the fact that we went a full circle from a particle nature of light to a wave nature of light to now a wave and particle nature, both of them. So the particles are called photons now. Mr. Einstein is the one who gave them that name, but it's still a wave. And when I say a wave, I mean a wavelength and a frequency. That's what waves are. So if we're wondering what is a frequency and what is a wave, well, I think we discussed this one before. So if I take a wave, doesn't matter which, and take a picture of it. For example, if I go to the ocean and see the water waves that they are forming on the surface of the ocean and take a picture, this is how a sine wave would look like. There are peaks in here, maximas, and there are minimas. Okay. So this is a peak, this is a trough. Okay. The distance between a peak and a peak, or a trough and a trough, is what I'm going to call as a wavelength, or from where the side crosses the equilibrium position, if I'm going from positive to negative, and I'm going from positive to negative. This doesn't count. I'm going from negative to positive, okay? So from positive to positive, negative, from positive to negative. Then in this case, also this one is wavelength. So wavelength, in the book, they use the Greek letter lambda for it. It's a distance. It's measured in meters. Or I could go on the same ocean, rent a boat, and be sitting on the boat, and the boat will go up and down. Up and down, it's going to bob up and down, okay? And if I count how many times did I go up and down in 1 second, that is a frequency. So the number of oscillations in 1 second, it's a number, okay? So this is what we call a frequency. So you're sitting on your boat, minding fishing or doing, and what you notice in here is that the boat is going to go up and down. So this behavior is in time. So this is what we call frequency. So this depends on that 1 second count, okay? So this is a temporal behavior, and this is a spatial behavior. Here, you take a picture with a camera, and you measure the distance. Here, you sit in the same spot, you don't move, but you allow time to change, because when you take a picture, you freeze time. Here, time is allowed to move, and you count how many that is. So this is a frequency, and this frequency is measured in hertz. So the frequency in the book, they use the Greek letter nu. I mean, it should not really have a tail in it. It should be like this. This is the nu, Greek letter nu. Sometimes you use the letter F, used also extensively for a frequency, and it's measured in hertz. The same Hertz that I mentioned earlier, who basically explained the work of Maxwell. I mean, he did a lot of experiments. He didn't have to explain it. Actually, Maxwell did a lot of explaining too. But the point in here is that the unit for a frequency, which is really a number divided by second. So a Hertz is 1/2, really. But in honor of Mr. Hertz, they give it the name of a Hertz. That's what you hear on your phone. They tell you you have a 5.5 gigahertz, or is it 2.4 gigahertz or megahertz, or that's what the station advocates when they're basically telling you what kind of frequency you need to tune in to receive their signal. So that is the same thing. Now, the product of this two is the speed of light. So this is c, the speed of light. So the product of this two is always fixed, the number, to be 300 million meters per second. So when I use these units, a meter and a hertz, which is 1/2, the unit has to be in meter per second. And the speed of light is not 300,000, because it's 300,000 kilometers per second. I have to convert it to meters per second, and a kilometer is 1,000, so it becomes 300 million meters per second. So this number that you guys saw earlier is in kilometers per second. So the speed of light really is 300 million meters per second, or 300,000 kilometers per second, if you wish. Anyway, so this is called the dispersion law. It's important to think about this law because the wavelength and the speed, they are inversely proportional to one another. I think we're going to come back to this one in here. So again, as the distance increases, the brightness drops. That's why when you go outside tonight, for example, and look at the stars, some of the stars are much, much, much brighter than the sun, yet they don't outshine the sun during daytime. There are some stars that are outside tonight. The same stars that you would see 6 months from today that are outside right now if you go out. But you don't see them. Why? Because the sun outshines them, because it's brighter than they are, although they're far more luminous. They produce more light than the sun does, but because of their distance, they're extremely, extremely far away, that the sun appears brighter. Because the brightness depends on the luminosity divided by the area of the sphere where you are. So think about it. This is the sun. Mercury will receive far more, will see the sun brighter than the Earth does. Venus will see the sun brighter than what we do, but it's going to be less bright than Mercury, and then the Earth does, because the Earth, the light before it reaches, it spreads throughout this entire big sphere. And I don't mean a circle; it's a sphere. So it's a sphere that expands in all space, not a circle. And the area of the sphere is 4 pi times this distance squared, which is the radius in this case of the sphere, this distance squared. So the d in here stands for the distance. So as you move back from the source, the intensity drops like 1 over distance squared. Because the 4 pi is just a number, okay? 4 times pi is what, like 12 something, okay? So that is the point in here. It drops like 1 over distance square. And this is exactly the point I was saying. I mean, if you are standing next to a person and the person is talking, you can hear them. If you move away, you can probably hear them, but not as loud as they were when you were next to them. And if the person continued to talk with the same intensity and you move even further away, you may not even hear them because the sound will propagate through a much, much bigger sphere. And for your ear that covers only a small area of the sphere, you're going to have a lower intensity reaching it. So it's not going to yank it as big as if you are close from it. So that's basically in a nutshell what this means. So again, when light hits an atom, atoms absorb energy. So atoms, basically what they are, I mentioned before. So you have a nucleus in here that's made up of a lot of particles in here. Some of them are positive, some of them are negative. This is the nucleus. There are protons and neutrons. And then you have the electrons. Let's take one electron for the particular, for my example. There are a bunch of other electrons in the lower energy levels, but I would just want to know about this specific electron. If the electron is at its lowest energy possible, the entire atom is sitting at the ground state because all of the electrons are exactly where they need to be. Then we are at the lowest energy state. This is called the ground state. Then if you excite the atom, there are different ways of exciting the atom. Either hit it with light, or heat it up, or put it inside an electric potential, or do something to it to make it not in ground state. So this electron in here, this is its ground state. This is where it's supposed to be, okay? But it could end up in here if it's excited, or end up in here if it's excited, or end up in here if it's excited. Any of these positions is a potential position for it, depending on how much energy you're going to. It's the same electron, by the way. I'm not drawing new ones. So in this case, it could jump in here if the energy that you give it is just enough to make it there. If the energy is actually more, it could end up in here. It could end up also in here. And it could end up also in here. It could be completely leaving the atom if it's high enough energy. In that case, you ionize it. So if you're hit it with super intense light, like the case, for example, or very high frequency that is more than what is required, you could ionize it and free the electron in the process. So the electron becomes free, and you will be left with an ion in this case. So this is an ionization process similar to the photoelectric effect that I mentioned before. But let's say, for example, it did not get free completely, but somehow it's still in here, but in an excited state. Not ground anymore. The ground is still here. So how does the electron go back once the excitation is removed? Then in this case, it could jump back straight down and re-emit the same light that it has absorbed, or cascade down its way, jump in here, and from here, jump all the way down. So in this case, it's going to emit two kinds of lights, either one which has less energy than the other, and this one has more energy because the gap that I drew in here is much bigger than this gap. But combined, they still equal to the original amount of energy. So the original amount of energy is much higher than each and every one of the individual ones. But if you combine them, you have the same amount of energy. Or it could cascade its way through 1, 2, and 3, or different combinations. This is 1, this is 2. So there are all kinds of combinations that you could end up with, where it could produce all kinds of emission light. So this light in here that is coming out, now it's emitted by the light. So it's going to emit it, but you could also absorb it. So light can be absorbed to excite the atom, or it can be emitted in an emission, basically, process. So the first one is an absorption or an emission. Obviously, you could excite the atom without having to run it through an absorption mechanism through light. You could excite it just by giving it heat, energy. or in a different fashion, for example, by putting it through the tremendous voltage. So it's not the only way of exciting an atom is running it through an absorption mechanism. You could do it in different ways too. But the emission is, in this case, is always going to be in the similar fashion. Okay. Okay, again, each atom has, that's why I drew in here so many of, depending on the Z number, which is the number of electrons in here. So that is actually, if you go and look at the periodic table, you will have hydrogen with 1 electron, helium with 2 electrons, lithium with 3, and so on and so forth as you move on through the periodic table, okay? Beryllium with 4, what comes in? Boron with 5, and then you have 6 for carbon, and you move through the periodic table, okay? So this is basically some of the chemical properties in here of the atoms. Again, you have to have the right amount of energy in order for you to absorb it. If you don't have that, light is not going to be absorbed. It has to really correspond to those transitions. So if light is too long, I mean too energetic in this case, for this particular example, then it's not going to be absorbed. It's going to go straight sail through and through. But if it's the right frequency between the two energy levels 2 and 3, then it will be absorbed. And then that light is going to be missing when you look at it from the other side. So the absorption spectrum is you hit gas, for example, with continuous spectrum of light. All frequencies are present. When you look at it from the other side, some of them are going to be missing. And it's going to be the same continuous spectrum, except that there are some dark fringes in here indicating that it's missing. There is another one probably that says missing. So this is what we mean by the absorption spectrum. Absorption spectrum is all light is in except some that have been captured by the material. Okay. Emission spectrum is the opposite. In the emission spectrum, basically nothing is there except some light that corresponds to that material. So you excite the atom and it's going to emit in those ranges. So let me open unit 22 for you guys. So again, I already delved into a little bit of the wavelength and the frequency and how they are related, and the formula that I've used already, the frequency times the wavelength. This is the wavelength, this is the frequency, is equal to the speed of light, is equal to 300 million meter per second, okay? And the energy carried by a photon, energy, is some number times the frequency. And that number happened to be just a constant, which is 6.636, 6.626. I forgot that if it's a 3 or a 2 in here, times 10 to the negative 34 joules times second. Times second. It's an action, really. Because remember, frequency is 1 over second, and second cancels second, so the energy is going to be in joules. Okay. So this is a constant. So h is just a constant. H doesn't change at all. This is a constant called Planck's constant. Okay. And then we're going to talk about the spectrum and the different bands of light. Okay. So again, in astronomy, it is far too difficult to visit stars. So the only way we study, that's why we really have to delve into this thing in here. How do we know about anything about all of the stars? It's light that we're receiving from it. Nowadays, we have another tool that is coming along. It's still not really well developed yet, honestly, to study all the stars with it. It's probably useful for neutron stars and probably also black holes, but not for regular stars, using the LIGO, which is the gravitational waves. But other short of this technique, which is really a novelty, the only way to study light, study your universe is through light. Period. End of the story. Okay. Now, when light is received, it tells us a lot about the star. It tells us its composition if we look at the spectrum. It tells us how fast it is moving if we see how it's shifting left and right compared to where it needs to be. It tells us about its size. It tells us how far it is. It tells us all kinds. It tells us about its history. It tells us about its future. We study a lot of things about stars just by looking at their light. I mean, if you think about it, the only way you can look at stars is by looking at the light they emit for you, whether through a telescope or the naked eye. So its light is, that's why we're studying light, actually. It's because of its importance. I mean, we can't reach this. So we have never sent a probe outside of the solar system. I mean, the only two right now that are barely leaving the solar system are Voyager 1 and Voyager 2, which were sent in the 70s. So just to give you an idea where these things are. So again, the wavelength, I described it as a behavior in space. So this is a spatial behavior, and we use the Greek letter lambda. So lambda, that's how you write, but you read it lambda, which is a kind of backward Y on its head, okay? So that's how you write it. It's a Greek letter for the wavelength. So the wavelength is distance between crest and crest, for example. That is what that is, and it's measured in meters, okay? Granted, for light, for example, it's too short. We don't really use a meter, we use a micrometer, even a nanometer. For example, for the red light, it's 700 nanometers. If you wish, it's 700 times 10 to the negative 9 meters. So if you want to use a meter still, which is what, 7 times 10 to the negative 7 meters. It's a very, very tiny number. Or if you wish, it's the same number, by the way, I'm writing it in different formats, 0.7 micrometer, which is a lot thinner than your hair. Okay, that's the wavelength. That's the distance between crest and crest for the electric field as it's coming using the red light, okay? For the blue light, it's even shorter, 0.4 times or micrometers, okay? It's even shorter than the red light, okay? So this is behavior in space and its wavelength, okay? And these are the examples in here. So the violet actually, which is kind of blue in this case, even the blue is 435, so I'm just giving a rough number. Light ranges between 400 and 700 nanometers. And the nanometer has the symbols nm next to them. So when you see a nano, that means 10 to the negative 9. Okay. And the color actually ranges in wavelengths. The longer wavelengths is red, followed by orange, followed by yellow. They are shorter, okay? So this is longer, from long to short. I'm coming down to shorter wavelength. Then green, then blue, then indigo, and finally violet. That's what the eye can see. Light extends way beyond this spectrum. So this is short, the shortest. And the other one is the longest. There is the ultraviolet, which are even shorter than the violet. The X-ray, which are even shorter than the ultraviolet. And the gamma rays that are even shorter than the X-rays. There is the infrared, which are even longer than the red. There is the microwave, which is even longer than the infrared. And there is actually the radio waves that are even longer than the microwaves. So that's the spectrum, okay? Everything. So again, the frequency is, they have you in here on a, on a tire going up and down. So it's a temporal behavior. And the law that I used in here so far is this law. This is an important law. It's called the dispersion law. And this is important. Let me explain why that is. Because you have lambda times the frequency. If you don't feel comfortable with nu, you can lose your letter f if you like, is equal to a constant number. This number never changes. On the other side of the equation, it's always 300 million. So if lambda is long, then the frequency is low. This is a case of red, for example. If you take the violet, for example, when lambda is short, lambda is small, the frequency is high. Okay, so you have to remember this relationship because their product, no matter what, has to be the same. So if you increase lambda, you better decrease nu in order for it to stay the same, and vice versa. If you decrease lambda, you have to increase the frequency. That is really what that is. It doesn't change. It's always the same. That product is always the same. And this is the other relationship that I mentioned earlier. If you express it in terms of wavelength, C is a constant number. This is 300 million. 6.63, yes, that's correct. So the way I had it, did I have it correct in the beginning or not? Yeah, 6.636. I think I have it a little bit more precise than what they posted in here. Anyway, so you have 300 million. And this number is a tiny number. This is Planck's constant, which is 6.636 times 10 to the negative 34. So this is just a fixed number. You take 3 times this number, and then you have the powers, you shift them and do all of that. So this thing doesn't change, divided by the wavelength. So longer wavelength will have less energy. Shorter wavelengths will have higher energy. In other words, higher frequencies will have more energy. Lower frequencies will have less energy. Because this number doesn't change. Each is always the same. And it's the frequency that really matters in this case. So as the frequency go higher, so does go the energy. That's why the X-rays are more dangerous than the visible light. That's why when you go for an X-ray chest, for example, or broken arm or something like that, the technician, the first thing he does is he goes hide behind the protective stuff that he has to, okay, to protect himself. Granted, in medical applications, you're only shortly exposed for it yourself because of the examination, but he is exposed or she is exposed on a more regular basis. That's why they really have to hide. They don't want to stay there because they do it day in, day out, and they examine a lot of people, so they build up that energy. The point being in here is the X-rays are far more energetic than the ultraviolet, which are far more energetic than the visible light, which is far more energetic, and so on and so forth. And the highest energies are for the gamma rays. Gamma, this is the Greek letter gamma, by the way. Gamma rays are the most energetic radiation. What I mean by radiation, electromagnetic radiation, EM radiation, because there are other kinds of radiation, for example, radioactivity, alpha particles and beta particles and things like that. So I don't want to confuse the two, so that we have that clear. Okay, if you run light through this is what Mr. Newton actually did, and actually it was known before him too, that if you run light through for example, a prism or diffraction grating, and I had one that I bought from Amazon a long time ago, that I probably displaced also. So if you have a diffraction grating in here, basically what you do, you break light into its own components. And this is exactly what's going on with the rainbow, for example. Rainbow. That's how what's going on. So particles of water suspended in the air, so usually you can see it after rain quickly, because there is more water in there, and as the sun starts to shine, the light is broken, it gets, first of all, refracted inside the bubbles of water that are suspended in the air, and then it's broken then into different colors, and then when it emerges, it's going to emerge back to you with light being basically divided into the different colors, all of the spectrums, the color spectrum that we were talking about earlier. What is it? Roy G. Give. Basically, you're going to see them. Okay, the entire spectrum. Okay, so That is basically and that is how spectrometers work. That is how we take light and break it down into the spectrum. And that's for some of you who are sitting in Astronomy 125, that's what we did. From, was it lab 2 or something like that? That's when we took a light source, which was a white source or a white bulb, a light bulb, and then we ran it through diffraction grating, and then we saw it made up of all kinds of spectrum, continuous spectrum. We ran filters, and we saw how it looks like. Again, the spectrum, I mentioned it already, that if you go from this side in here, it's the wavelength. So radio wave are much, they're of the order of hundreds of meters or even more kilometers, actually, okay? And they're used for telecommunications mainly, like, for example, your cell phone and for your whatever, all kinds of things in there, okay? Cell phone is actually slightly lower, but it's still, I mean, if you think about it, your cell phone is at 5 gigahertz, so 5 gigahertz, you can find now how much the wavelength is for your cell phone. So lambda is, remember, lambda times the frequency is c, and the frequency is about 5 gigahertz, and giga is 10 to the power 9 hertz. And the wavelength then time is equal to 300 million, or 3 times 10 to the power 8. That's what 300 million is, because you have 8 zeros. Okay, 6 zeros for a million, and then plus 2 zeros. So basically, the wavelength is going to be 3/5, and 8 minus 9 is 10 to the negative 1. So 3/5 of a 10 to the negative 1 of a meter. So if I multiply this by 2 and multiply this by 2, so I'm gonna by 2 times 3 is 6. So it's gonna be about 6 times 10 to the negative 2 meters, which is 6 centimeters. And 6 centimeters, we'll put it somewhere in here. Because remember, this is a millimeter, 10 millimeters, which is a centimeter, 6 centimeters somewhere in here, because this is a meter. So this is your 5 gigahertz where it's going to be. So cell phones, police radar technology, microwave devices, they're all using that. TV and FM, they're using in the order of a meter. For longer wavelengths, you use the radio waves. The infrared is the thermal detection devices for imaging, because you and I were emitting that range. So this is the infrared. TV remote control also uses that range. And then this is the visible light. This is what your eye and my eye are sensitive to. It starts from red and goes all the way to violet. And this is the entire spectrum. I mean, it looks big in here in the bottom, but it's not really that big compared to the rest of the spectrum. The UV radiation, which is dangerous, and because the Earth has this protective layer, which is called the ozone, and because the ozone interacts with the ultraviolet radiation, so it takes it in it and converts it back to a normal oxygen, and then it's going to combine again to find to have an ozone. So the ozone layer plays a role in protecting the Earth from this dangerous radiation. Ozone, by the way, is just oxygen, except has an extra atom in there. The rearrangement of the atoms is a little bit different than normal oxygen that we breathe, which is O2, okay? Then you have the X-rays. X-rays is what's used in hospitals, and this is a very, 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 very high energetic, because as we go from here on the blue line, we're going into increasing energy, and in this case, shortening the wavelength. Gamma rays are far more energetic, and they come in gamma ray bursts. Sometimes they're emitted in the basically during violent events such as supernovae and some other events that causes them to exist. Pulsars emit the X-rays. Pulsars are neutron stars that spin super fast on their axes. And then the sun emits in the visible range for the most part. As a matter of fact, the sun peaks around the green. And because a combination of all of these colors exists in the spectrum, because of Wien's law that we're going to discuss shortly, the combination of the lights appear to be white, okay? And then you have other interstellar clouds. They emit they observe actually in the infrared. And this is where the James Webb is operating right now, in the near infrared and operation. So this is where the James Webb is operating now. The Hubble telescope was operating a little bit in the infrared and also in the little bit in ultraviolet, but mainly in the visible. So that's why these two telescopes have actually different view, or at least different kind of perspective on the universe because of the way that which frequencies they are going to be operating at. So the James Webb sees things we can see. Okay, and then you have the cosmic background, the microwave background. That's actually, remember, the universe, and if we're going to have this down the road, evolved from a super hot, basically, state to a more, basically, right now, it's a very cold universe, which is a little less than 3 Kelvin. And the initial frequencies, they were very high, but because of the Doppler effect, which we're going to explore in Unit 25, the frequency was shifted all the way to the microwave. That's why the James Webb was developed in this range, because we know that things that emitted light a long time ago is Doppler shifted toward the red. As a matter of fact, it moved way beyond the red. Now it's in the infrared or probably the microwave. So this is the cosmic background radiation, the CMB. And we're going to have more down the road on the CMB. We're going to talk about that and the active galactic. They emit in the radio wave because of the distances involved. So this is in a nutshell the spectrum of light. And we just talked about all of them. I mean, here's just a continuation of the gamma rays, the X-rays, and all of that. And of course, as I mentioned already, different telescopes, whether Chandra, whether James Webb, whether the Spitzer, whether the Hubble telescope, now they have different views of the universe as they see. In this case, the radio waves, the same galaxy, by the way, it's the Andromeda galaxy. And Herschel, in this case, this is the different wavelength. This is the infrared. Okay, this is between 70 to 250 micrometers. This is of the order of a 6 centimeters. Now for the visible lights, this is how Andromeda would look like to you and I with the naked eye. And then this is the Swift, which is operating between 160 to 330 nanometers, which is extremely short wavelength. Okay. And then you have the X-ray in this case, which gives you a different view. Where are the high energy emitting for X-ray radiation from the same galaxy? This is the same galaxy. Okay. So this is units 21 and 22, which are part of this exam that is coming down the road. So I hope that you guys will have no problems with them. And again, watch for this recording that I'm going to be posting hopefully this weekend. If you don't see it by Saturday, please shoot me a message saying that you promised to have that homework. I hope that this is good. Any questions? Okay. Thank you.